Thank you. So this was actually a fairly small project on the scale of projects at Standard Chartered. It was just 3 months' work, although putting it into production took a lot longer. But it was a small project that was quite easy to talk about. It doesn't involve any banking, and I thought it would be good to talk today about something that we do at Standard Chartered, something that I did at Standard Chartered. But we do lots of things. This is one example. We don't just do DSLs all day. So what is KDBQ? It's an array processing language or used for programming this proprietary column store database by KX Systems. It's very commonly used in the finance industry, often for sort of for time series applications. Q is the language that we're targeting here. I guess it's the SQL analog in the KDB world. It is famously terse, so when they do a folding queue, there's an infix operator for folding. Very, very terse, and Q programmers don't even like white space, so they like to write all things on one line with hardly any white space. They don't like, it's dynamically typed as well. Q is syntactic sugar on something called K. That's why it's called KDB, because the database itself is written in K. K is descendant from APL and other things. And there are variants like A+ used at Morgan Stanley. And so Q is what we'll be targeting in this talk. And why are we doing this? What's the problem? We have a significant amount of Haskell logic that needs porting to KDBQ. So we'd written, I can't talk about what the logic was, but there were thousands of lines of Haskell code, very, very complicated Haskell code that was dealing with taking market data and smoothing it and averaging it. And we had, we were told that we can't really do the whole thing in Haskell. It was prototyped in Haskell because Trader had an idea. It was written in Haskell very quickly and went live very, very quickly. The traders like Haskell and they like us because we do deliver things very, very quickly. But the overall sort of strategy for the bank was not to have this sort of code in Haskell. They wanted it in KDBQ, which I guess they wanted to backtest quite a lot, and it's quite good for backtesting. You can replay. They have all their data in KDBQ, market data, and they can replay this over the data. So I was tasked with porting all this to Q, and of course Haskell is my golden hammer. So, but what I found was that there were problems with manually porting Q. I'll talk about that on the next slide. But certainly Haskell is, as we all know, aggressive enough to enable the composition of Q programs within Haskell itself. And this is the idea of a deeply embedded domain-specific language, or a deeply embedded EDSL. And I believed that this would be a fairly cheap solution. The alternative would be a kind of a back end to our Haskell compiler that targeted Q instead of the bytecode that it does target, but that would have been a much more expensive position. And also, I always try and put a little bit of category theory in every talk I do. So the rationale for the DSL. So why do I think this was a good solution, or why did I choose this solution? And it was really that I wanted Haskell syntax. I didn't want to port this code. To manually port it, I'd be writing in Q, and I would lose lexical scoping. I would lose standard operator precedence rule. Q does not have those. That would mean that I would be doing essentially manual transformations of the code, because the Haskell code made heavy use of closures, and that would have been tricky to do those by hand. But also, I get to choose the semantics within EDSL. I can have static types, I can have referential transparency, null safety, I can have IEEE compliance. Q doesn't have that. This is something I discovered. It's not. It's not really about the fact that we're doing lots of floating point ops in Q. It's more that for example, the relational operators in Q are not IEEE compliant with respect to nans. So it's sort of more the edge cases that I hit. But also, a big thing is that Q has these expression size limits. The interpreter's designed to run very, very fast and make use of, I guess, L1 cache on the CPU. You only get about 32K, I believe. And for that, it has really restrictive limits. Like it's a very small, you can only have a relatively small amount of code inside either branches of a conditional, for example. And you can, and there are limits to how many global variables you can read from a function, or how many local variables you can have in a function, and limits on the parameters in the function. Lots of limits, and of course all the Haskell code that I would be porting breaks all these limits all the time. So I would have to be doing manual transformations to port this code. So why not automate that? The other great thing about an EDSL is we can use types to document the interfaces and machine check correctness. Again, the dynamically typed guys tend to think about, they don't think in terms of schemas, and they tend to say, here's an example input, and here's an example output. And you see all this you see this often with the web services world. And you know, here is, and I didn't want to say, I didn't want to, because I had to interface, the code that this generates has to interface with other stuff written by the Q team, and I wanted to say to them, this will be what I give, this structure, and I will be expecting this, and I wanted to type, you know, a schema essentially. And I also wanted to evaluate Q programs using Haskell as well, because the KDB requires a license per machine, which is, you know, in a bureaucratic bank, is very difficult to get hold of licenses. And so if we have a continuous integration server running tests, or other build servers running tests, and even it's very hard to get licenses for these machines. So I can't even test the KDB code on these machines. So it would be great to have an evaluator in Haskell that would do that. It's also, there are other reasons to write an evaluator as well, which I'll talk about. And also mixing Q programs with Haskell code inside the same file. Again, it was very good for testing. And I like the idea of having a safe and restricted subset of Q, which is what an EDSL can provide. For example, we have no need to be Turing complete in the problem we were trying to solve. So let's get rid of that. And there are other static checks there are lots of static checks I could do, although I could think of lots, but in the end, I'm not doing actually that many. And this may disappoint some people. People get a lot of people that know Q got all very excited in the bank when I said I'd done a DSL in Haskell for Q, because they were thinking of the query side of Q and the bulk operations, and that's not the problem that I was solving here. So if you think about LF or fold LF, I'm doing a DSL to implement the function that the bulk operator takes. So I wasn't concerned about giving types to bulk operations or queries, which is a much harder problem. And I do think Haskell has got some, certainly capable of taking this on. And Leonard, who was working for us at the time, did a paper where he gives types to the relational algebra. Jeremy Gibbons has a paper on Neperian functors, which are, again, talk about lifting scalar operations into bulk operators. But I didn't need to do any of that. So it's really, I'm tackling an easy subset here. Key features of the language. We have expressions and statements. I did want some side effects. There's a few cases where some mutable references were good for performance. There's a few cases where I wanted to log. And there's a few cases where I wanted to export a binding for external Q code, or import a binding. And there were a few other areas where I did want some impurity. So I have statements as well as expressions, which is a bit of a shame, really. perhaps I was too lazy there. I could have possibly avoided that. But the advantage of differentiating between the pure functions and I call them procedures is that I can, there's lots of optimizations I do, like partial evaluation and other things, and those which are very easy to write for such a small DSL that it's nice to know that it's safe to do that. So I statically differentiate between something that's a function and something that's a procedure. We also, although I do recover some sharing, I'm not going to talk about that. I don't do anything clever. I mostly rely on explicit sharing, though, to get the manual control. So there's a let in the language. Leonard, just before he left, had suggested to me that I have this, that I overload the language, make it all polymorphic, the whole lot, and then I can get an evaluator for free, kind of a shallow, deep polymorphism. Given the looming deadline I have, I didn't attempt that. I just, there's nothing fancy like that. So sorry, Leonard. So here's some examples of the EDSL that I'm going to run through. We have, this is where an example of how a mathematical expression can look a lot nicer when you have the operator precedence, and that's what it looks like in Q, because we have to, put lots of these parens everywhere. This is how we might construct composite data. So we have the record syntax, which at least the syntax is good. In Q, you have to sort of build two vectors and then use this bang to join them into a dictionary. And I found this incredibly error-prone, because if you get the order wrong, there's no types here either. So I found this incredibly error-prone. And you can imagine in a real-life production system how big some of the records get. So this I think is really surprising why they haven't come up with anything better than this. Records are of course declared, so there's a type associated with that term that I showed you, and these guarantee the presence of fields. So although we might compile that into a dictionary, in the DSL it's a record because we know that it's going to succeed if I read a field out. We also have a little bit of template Haskell here to generate some machinery, for example, lenses. So this lens here is a generated lens. Here's some code in the DSL. Notice that that's a closure there. Can't do that in Q. We use sum types a lot to for options, I've handled enum as a special case where you can have something that looks a bit like a switch here. There is an exhaustiveness check that's done at staging time to check that you have provided all the cases. So it's not done by the GHC compiler, but it's done by the EDSL compiler, and that's what it would look like in Q. You'd always have to have this impossible case here. And now some types are I generate a fold function. Because I can't pattern match. I'll talk about that a little bit later. But this template Haskell here generates a fold function called elim, and here I've just we have something in the prelude for this DSL that just like the Haskell either, and it's written in terms of this eliminator here. And this is the explicit sharing. So it's a let Q expensive computation that I want to explicitly share Y, and this gives you this graph essentially in the AST. And this is how I would do an impure computation: create a mutable reference, play with a reference, and yeah, it has a monad Q prog, fairly simple. And now to talk about some of the techniques which I used, and I'll try to comment on their effectiveness as well. So of course, what I was doing was a deep embedding. So there's a syntax tree. This is only part of it, but there's a syntax tree to represent the terms. And obviously, once we have a syntax, we can analyze, optimize, and compile it. And we make use of Haskell's very good overloading. So we can use type classes, type class instances for num, for example, and fractional. And we can then do write 1 plus 2, which is completely polymorphic, and then we can resolve that by constraining the return type to be Q double instead of double. And now that 1 plus 2 would give us this AST. So it works quite nicely. Functions are, of course, a bit harder to reify, and for that I use this pretty standard technique, higher order abstract syntax. This is often talked about because it can reuse the abstraction and binding from the host language. But here I'm using it as a simple technique to reify the functions. So here you see to create a Q lambda, there's just a constructor that takes a function in the host language, QA to QB, and then returns the function that's been embedded. So this is a very simple lifting operation there. But the problem we have, I've said beware of exotic terms here. The problem is that you can no longer perform case analysis on any types used as inputs to your binding function. So you can no longer, because of course you have it's fine to refer to it symbolically, but it's actually a syntax tree. So you can no longer perform pattern matching on it. And an exotic term would be one where you did pattern match on the AST in the definition of your your function here. No. Yeah, I tend to fairly. I've kept it pretty simple, and I mean even using GADTs is further than probably go. I've kept it pretty simple, but sorry.
Are you then in charge of writing those, like what those functions do?
Yes.
Rather than having random users kind of write them, so you can avoid writing exotic terms yourself.
I see your point. Well, they wouldn't to pattern match on, I suppose, because as long as that type's not, as long as the constructors for that type are not exposed, it's an abstract type, then they just wouldn't be able to pattern match on it. So it's not exporting those constructors you saw in the AST. So these constructors, they're and essentially those primitives used to implement the prelude. They used to implement a prelude that is exported. So you only get access to primitive functions you can use. So here are some statements. We have some instructions to create a new reference, read a new reference, write a new reference. I have instructions for logging. I have instructions for exporting symbols into the Q runtime and importing symbols from the Q runtime and all these sorts of side-affecting things. And I used something called the operational package to reify the monad, because of course what I want to do is I want to write I want the user to be able to do notation, do their side-affecting stuff, but I want to capture that as a syntax tree, so I want to reify the monad. And of course the free monad has these problems with asymptotics, and again I was pretty lazy, and I just used the operational package that solves that for me. A bit like a printer solves the concatenation problem for you. This has a surface API and an internal representation, and the left associated binds aren't a problem with operational. It does differ in some ways to a free monad in terms of how it deals with laws and things like that. But essentially, it's the same thing. And when I get my reified program, I use these constructors to view it. I can see the binds and see the instructions, and every program is terminated in a return. And this is really easy to use. I didn't need to read any commit blog posts to do this. So metaprogramming is almost it's a first-class thing in an EDSL. The embedded functions are almost second class. There's a function in the host language to create an embedded function, and another function to apply an embedded function. But these functions, what I'm calling meta functions in the DSL, these are just sort of, of course, host language, plain old Haskell functions, and those are very easy to work with. So you have the situation where a lot of the time you're actually metaprogramming. And that does have some advantages. It causes problems you can get code explosion, and that's why often you need to try to recover sharing. But it does have some advantages. So here are some advantages. The Haskell code that I was porting made heavy use of lenses everywhere. But it wasn't actually using lenses in any kind of first-class way. It wasn't storing them in state and then later at runtime retrieving them. So the lenses could actually be represented as they could be computed purely at staging time. So as a form of metaprogramming. So our lens library has this is the data constructor for a lens. And you can there's a get function, a set function, and a compose, and you can see really it's just a selector function. You can think of it as a selector function on that piece of data there, and it just gives you back a plain old function f to a, and the setter l. You can think of that as a selector on that chunk of data there that gives you back a function aff. And so I can just use these, although there's nothing specific, there's nothing about this that is part of the DSL. These are just normal Haskell functions, but I can use them in the DSL to get, to have lenses, but that are evaluated at staging time. And another example is a reader monad. I can again, the Haskell code made use of a reader monad, and that again is something that there's just a plain Haskell function here, and there's no reason why I can't thread these values through at staging time. Essentially, because it wasn't being used in a way that would need a first-class representation of this. And the nice thing about both the lenses and the reader in this case is that they had no runtime cost to Q, because of course these things are very cheap in Haskell because of the optimizer is so good. But when you compile to a target like Q, these abstractions, something that the F# and the Scala people sometimes find, that these abstractions can have a much bigger cost, and they would definitely have a huge cost if they were represented at runtime in Q. This is also this turned out to be quite important, having a dynamic type, because I was interfacing with code written by Q developers. So I wanted a type that anything that I got from the outside world, from them, I wanted to have a kind of a safe unpack, which would where the type would be scrutinized. So Q does allow you to query a type of a term. You have to there's a kind of a table. It gives back an integer, and you have to go to their website and look up what the integer means. But you can, all types that come from the outside world come via this dynamic, and I unpack them and scrutinize them. It's quite important because one thing dynamic programmers often do is they can change the type all the time. So in fact, there's a Q library to talk to the network. And if a single item comes down the wire, gives you just the item. If 2 items come down, then suddenly you have a list of 2 items. Yeah, so the types can change. And this helps guard against that. And I used Quick Check. We're big fans of Quick Check at Standard Chartered. And I almost had to use Quick Check because my colleagues would say, well, why aren't you using Quick Check if I didn't? So I use Quick Check to generate and interpret random expressions. And then I came up with properties that must hold, like for example, algebraic laws. I built an evaluator to use it and verify the assumed semantics and also verify the output of the compiler. So here's a nice diagram, I think, where if we start with terms in the DSL, there are 2 ways to get values. I can obviously compile and then use the Q runtime to evaluate the Q program. So I can compile to Q and then there's a Q runtime to evaluate the program. Or to get a value, I can just go straight through the Haskell evaluator. So what I want, of course, is equivalence between these 2 values. So in building tests that go both ways, I'm testing not only the compilation pipeline here, I'm also testing my knowledge of this, which is only an assumption because it's not really formally written down anywhere. My evaluator in Haskell here represents my assumed knowledge of what Q is doing.
So that evaluator in the bottom is not something you wrote?
That's from KX Systems, yeah, and it's a black box, and it's not really well specified what it's doing, yeah. So the quick check tests I'm doing here, where they go down here and there, I'm really testing both this and that. So I did this, as I said, by generating random expressions. Although I got all sorts of suggestions that why don't I, interleave type checking and all the sorts of things, I didn't have time, and so it would be quite tough to generate expressions of arbitrary. There are papers on this, but I didn't go there. Instead, I just constrain the type to various things. So we had expressions involving dictionary operations, expressions involving list operations, double arithmetic with biasing infinities, nans and zeros, making sure that those edge cases were well represented. And so here's some techniques, more techniques I used for embedding algebraic data types. There was a class to lift an arbitrary literal into a Q, into the Q world. And you can see there's instances, records here. In practice, I wrote some template Haskell to generate these things for you, so you didn't need to write them. And then we had a projections using the of a tuple. So this, of course, is not a Q. The entire argument as a pair of syntax trees, so that enables me to pattern match on it. I use the view patterns JSC extension because I'm out of date, and there are pattern synonyms now, and you could do an even nicer job of that. Eliminators, well, that was for product types. For some types, we need something a little bit more complicated. We need to generate fold functions, as I showed you in examples. This class has an associated type because the fold function has has an argument per alternative, per case alternative in the sum type. So you can see for maybe there are two here. There's that alternative and that alternative. Yeah, these, again, there's template Haskell to generate these. Problem, okay, so closure conversion. So now, for the last part of the talk, I was going to show you one of the more thorny parts. Generally, it was pretty easy to implement this DSL. I think my intuition that it would be fairly easy to do was correct, although there were some thorny problems. So this is one of them. In fact, the hardest one. So there's a significant amount of Haskell code I've talked about that makes heavy use of lexical scoping and closures, and Q, as I said, does not support those. But Q also has expression size limits, and I talked about the branches of a conditional. But that we can work around quite nicely by doing a simple eta expansion and lambda lifting, a bit like the join points that Simon was like that. But both these things require us to basically transform the AST to remove lexically captured variables. So a very simple way of doing this, there is a very simple way of doing this because Q does support partial application. And we can, there's a very simple way that we can close all the open lambdas by calculating all the free variables bottom up. I'll show you on the next slide. And captured variables to the parameter lists and partially apply the additional arguments. It's best shown with an example. So let's say we have this. In the inner lambda here, x is essentially a free variable of this body here. The binder for it is outside in the top level lambda, and this isn't supported in Q. But this is supported, where we can basically close this lambda here by adding the x as an explicit binder, and then partially applying this inner lambda, partially applying x to this inner lambda here. So this now is supported in Q. But all is not well. Sorry. Next slide. Here is an implementation of this. It's fairly simple. We have a little auxiliary function here, free variables, that calculates the free variables, gets a set, takes away the arguments from that set, and then adds the free variables minus the arguments to the argument list here. So it's essentially this code is doing what we were doing there. But this free variables call here is of course a fold on the syntax tree. It's going from qexpr to set of var. So essentially, this is a naive piece of code. We have a potentially quadratic complexity here. We also would like to avoid specifying every case because obviously we've got q lambda here, but many other cases that don't concern us. So my one thing that I've been using for many years, and I use this at Barclays, and all the chaps that are doing Haskell on the FPF team use this, was using functor fix points and recursion schemes. And I like them because they add principled structure to our traversals. We can get compositional data types and traversal code. We get to use foldable and traversable, which help us avoid boilerplate traversal code. And it's based on this idea, fixed points of functors. And because you parameterize recursion, you can swap in other types in there. So you can. It's very easy to annotate your AST. For example, every point of recursion, or it's very easy to add recover sharing, or there's lots of applications. But it does mean that you've now got a functor, and you have to use this sort of type level fixed point here to give you to recover back the recursive type. And most of what you need is pretty much all you need most of the time is a catamorphism, which is a generalized fold. And I've got some references to learn about it at the end of the talk. But it has a very simple type signature. It's essentially you can write it for any functor f, and there are lots of variants of kata, just as there are variants of fold, like MapQML. Lots of variants of kata, but you only need to write them once. You can write them once for any functor, and you can also you can also traverse top down by folding to a function that you can then run. I quite like this, that you can read off the definition of the catamorphism. So if you imagine you've got your fixed functor f, and you fold to some value here, that's kata-alg. That's what takes you that way. But what's the definition of that? Well, we can unwrap fixed f1 level by unfixing, so we can go up here, and then to go from f of fixed f, where our AST nodes are all contain fixed f's, we just f-map kata-alg to get to fa, and then the algebra, which is this fa to a, takes us down there. So we can go up there, which there, that's the right-hand side of kata-alg, which I think is quite nice. And here is an AST that's a functor. This one is used for all the optimizations and recovering sharing and so on, and that doesn't use HOAS, of course. We've converted out of HOAS, higher order abstract syntax. So now we're going to use a zygomorphism to factor out the free variable calculation as an auxiliary algebra. So we have a main algebra here, which scrutinizes, contains expressions and the free variables that the descendants have. And then we have another auxiliary algebra, which is the free variables algebra. At each level, the free variable algebra, if you like, is providing this input here. So we just write close as zygo this algebra and that algebra. It's semi-mutual recursion. You can study this at home, but the point is it's just a catamorphism. It is just adding structure, just like MapQML adds structure to a fold. This is just a catamorphism, really. That's all it is. But it does let us split these two things up and separate out the concerns without that quadratic blow-up that we got when we were just nesting the folds, which is as a separation of concerns. And also we get the minimal boilerplate because we're able to, for example, use fold here. So set is a monoid, and we just need to consider the variable case and the lambda case, but then all other cases we can just use fold, and that's obviously because E is a because Qx per f is a functor, that works out. So we get order and complexity, separation of concerns, and minimal boilerplate. But there's still a problem because Q has a limit of only 8 function parameters. Therefore, this technique won't work because the Haskell code used loads and loads and loads and loads of free variables everywhere. So this limit, we would run into it. So we have to do something a little bit more complicated. A single environment, which is a linked list of frames, single environment identifier added to the parameter list, and then we need any free variable references have to index into that environment. But at least the free variable calculation doesn't change, but or the free variable algebra doesn't change. This main algebra has to change a little bit. Now it produces a function. Now the catamorphism produces a function which, when given an initial empty environment, will pass that down. And you can see here where we build Lambda, there is a single env-ID, environment ID, added to the argument list. Like all the and to index into that environment, and that environment do that. We can down to all the ones that are not Q or Q the functor. So that's you can have a closer look at that at home. But so the conclusions of the talk are that EDSLs, I believe, are quick to build relative to other generation techniques. They do let us take back some control over syntax and semantics as long as we're happy with Haskell syntax. But yes, the semantics certainly, we've given Q all the semantics that we love in Haskell, the referential transparency and things like that are, we've mainly null safety, we've IEEE compliance, we've recovered those semantics. This was invaluable though, having my evaluator to test my assumptions about what Q was doing. That was invaluable. And also, this is not the first time I've used recursion schemes, but I continue to be convinced that they are a very principled and effective way to structure traversals and to lessen boilerplate. One thing, though, that wasn't so good with EDSLs is that it's very difficult to generate readable code. The names are mostly all generated, so the Q code looks absolutely horrible. You can mitigate that by allowing users to comment, to add in string comments, but it is a problem, and I had comments from the Q programmers that that they're just amazed that what they see works, because it's just it's completely unintelligible, the code it generates. But it's fast enough, and it's correct. Once I sorted out the IEEE compliance assumption, the code the Q generated code agreed perfectly with the Haskell one with all the backtesting. And there are some references to look at, and there's the slides. I'll stick the slides up. Thank you very much.
Okay. We're pretty close on time. We can probably take one or two questions. So,
what's the performance difference between the original code, your QDSL in the evaluator, and the Q code itself?
I was hoping you weren't going to ask that. It's basically it's basically about the same speed as the mu code. Maybe even sometimes a little bit slower. So it obviously Leonard is a great compiler author, and so I'm happy to be almost as fast as his stuff. But yes, essentially this is solving a very difficult problem because the code was never written for Q in mind. It was written in Haskell in mind, and we do all these transformations to make it even run. So I'm happy that it's fast enough, but it is sometimes slightly slower than Haskell code. Yes.
I was just going to ask if you have a slide with some code that one of your users would write. Did you have that earlier on at all?
I couldn't show it. I mean, my users would be other strats.
Yeah, right.
But it basically looked to convert the code to the DSL was really just a case of changing all the pattern matching into folds, changing lets to the explicit let Q. It was fairly mechanical transformations, and there is some code in the monad that does side effecting stuff at the top level, but most of the code is pure. Yeah, I'm sorry I couldn't show more of the DSL in action, really, but there were thousands and thousands of lines of code in this DSL.
Cool. I think we should wrap up there. So let's thank Tim once more.
Thank you.